At 07:18 UTC on August 15, 2026, the ground beneath Lingualasa cracked open. A magnitude 3. 9 earthquake tore through the road near the Bruneck Refuge, splitting asphalt and forcing an evacuation at Piano Provenzana. Within hours, Italy's National Institute of Geophysics and Volcanology confirmed what local seismologists had already suspected. The Pernicana Fault, the single most closely watched tectonic structure on Mount Etna, had reactivated. Over the following 5 days, 13 additional earthquakes rattled the same stretch of ground. None of them were large by global standards. All of them mattered enormously to the people who study this mountain for a living. To understand why a cluster of small quakes under magnitude 4.0 sent Sicily's Civil Protection Agency scrambling, you have to understand what the Pernicana Fault actually does. It isn't just another crack in volcanic rock. Research published in the journal Communications, Earth and Environment, part of the Nature Group, established that this fault functions as the northern rail guiding the slow, continuous eastward slide of Etna's entire unstable flank. Picture the eastern side of the volcano, not as solid, fixed rock, but as a colossal, slowly creeping mass sliding toward the Ionian Sea inch by inch, year after year. The Pernicana Fault marks the boundary along which that sliding happens. When it moves, it isn't behaving randomly. It's registering stress transferred from deep inside the volcano, stress that has to go somewhere as magma pushes upward and the flank above it responds. That's precisely why INGV describes the fault as a sentinel structure. Its behavior tracks two very different processes happening beneath the surface: magma inflation, when rising molten rock pressurizes the interior of the volcano and pushes the flank outward, and post-eruption deflation, when that same interior empties out and the ground above it settles. Both processes can trigger movement along Pernicana, which is what makes interpreting any single reactivation so difficult. A shift along this fault could simply mean Etna is letting off pressure after an eruptive pulse, or it could mean something more consequential is building underneath. The current reactivation arrived at a genuinely complicated moment for the volcano. Etna had already been erupting on and off for most of 2026, starting with a fissure vent that opened in the Valle del Bove on New Year's Day. That eruption faded, flared again in June near the Valle del Leone, and then escalated sharply on July 30th, when Strombolian activity at the Voragine crater intensified so quickly that the Toulouse Volcanic Ash Advisory Center pushed the aviation color code all the way to red, its highest warning level, after an ash plume climbed roughly 7 kilometers into the sky. By early August, a new eruptive phase had opened multiple vents simultaneously, one near 2,950 meters elevation, another near 2,360 meters, both feeding lava flows down into the Valle del Bove. It was in the middle of this ongoing multi-vent eruption that the Pernicana Fault let go. Historical precedent is exactly why volcanologists are watching this development so closely rather than dismissing it as routine. Reactivations of the Pernicana Fault system have coincided with 3 of the most consequential volcanotectonic episodes in Etna's recent history: an intrusive seismic swarm in 1984, a destructive eastern flank episode in 2002, and another major intrusive event in 2018. All 3 involve powerful magma intrusions beneath the surface, an acceleration of the eastern flank's movement, and earthquakes strong enough to cause structural damage. The 2002 episode is a particularly stark example. The fault's reactivation that year triggered the Presa landslide, a slope failure that damaged lifelines and buildings across the northeastern flank of the mountain. None of that means the current activity is guaranteed to escalate the same way. It does mean the fault has a documented history of being the first visible sign that something larger is happening underground. That ambiguity is precisely what INGV flagged in its own communications following the August rupture. Officials were careful to describe the situation with genuine scientific uncertainty rather than false confidence in either direction. Historically, the fault's movement has occasionally preceded lateral eruptions, meaning new vents opening somewhere other than the summit craters, in addition to simply marking a normal transition between phases of an ongoing eruption. In plainer terms, this could be Etna resettling after weeks of eruptive activity, or it could be an early signal of a lateral vent preparing to open somewhere along the mountain's flank. As of the most recent monitoring updates, seismologists don't yet know which explanation is correct, and they've said so plainly rather than pretending otherwise. The physical evidence on the ground reflects that uncertainty in very literal terms. Regional reporting on the August 15th earthquake described fractures opening directly across paved roads in the fault zone, severe enough that authorities closed a section of the Marineva road running through the affected area. Sicily's Civil Protection Director, Salvo Cozzina, directly attributed the observed surface deformation to the fault's movement, explaining that earthquakes along structures like Pernicana tend to occur at very shallow depths. Even without reaching a particularly high magnitude, Shallow depth means the shaking is concentrated close to the surface, capable of producing highly localized but visible damage. Cracked pavement, disrupted infrastructure, fractured buildings, precisely along the roads and structures that happened across the fault line directly. It's worth pausing here to separate what's confirmed from what's still speculative, because volcanic hazard reporting has a well-earned reputation for drifting toward exaggeration. What's confirmed? INGV has verified the Fiandaca Fault's reactivation using its own seismic monitoring network. The earthquake swarm between August 15th and 20 produced 13 recorded events in the Lingua Glossa area, all below magnitude 3, plus the initial magnitude 3. 9 shock that opened the sequence. Road damage and evacuations at Piano Provenzano are documented by multiple independent outlets, not a single unverified source. What's still uncertain, whether this specific reactivation will precede a new lateral eruption, continue as a routine part of the current eruptive cycle's wind down, or simply settle without further escalation. INGV's own language, genuine scientific uncertainty, is the most accurate framing available right now, and any version of this story claiming certainty in either direction is overstating what the data actually shows. Understanding the broader eruption. This fault activity as embedded in helps clarify the stakes. Etna's 2026 eruptive year had already been unusually active well before the Fiandaca rupture. The Christmas Eve 2025 eruption sent lava flowing from the southeast crater down to roughly 1,160 meters elevation, close enough to altitudes where guided lava viewing tours normally operate, prompting new safety restrictions across the tourist industry that depends on the mountain. The New Year's Day fissure that followed opened at the foot of Mount Simone, an ancient extinct crater within the Valle del Bove, sending lava flows steeply down the eastern slope, close enough to the villages of Milo and Fernazzo that early images circulating online sparked considerable public alarm, even though INGV maintained there was no immediate danger to residential areas. By summer, the pace had only intensified. The eruption that began at dawn on August 6th evolved rapidly. Strombolian activity at the Voragine crater, a lava flow reaching toward the northeast crater, a lateral vent opening near 2,800 meters, and then, just 2 days later, an entirely new fracture opening at 2,500 meters elevation. Observers describe this sequence as signaling the extreme fragility of the north face of the Valle del Bove and the eastern side of the volcano more broadly, language that, in hindsight, reads almost like a direct preview of the fault activity that would follow 1 week later. Volcanic tremor readings tracked this escalation closely, with INGV recording a sudden increase in average tremor amplitude beginning around 19 Tsuru UTC on August 10th, climbing to levels high enough to prompt sustained monitoring through the following days. The disruption to daily life and regional infrastructure during this period was substantial enough to draw national political attention. Catania Airport, sitting directly in the path of ash plumes generated by the ongoing eruption, faced what regional officials described as the worst Etna-related crisis in 24 years, with flights repeatedly diverted to Lamezia Terme, Palermo, Trapani, and Comiso airports throughout the peak of Sicily's summer tourist season. That disruption became consequential enough that Italy's transport minister raised the question of relocating airport operations entirely. A striking response for a volcano that erupts as routinely as Etna does, and a sign of just how significant this particular eruptive cycle has been compared to recent years. Amid all of that, the ash and lava captured most of the public attention, for obvious reasons. It's visually dramatic, it disrupts flights, and it's easy to photograph. The fault reactivation received comparatively less mainstream coverage, despite arguably carrying more long-term significance for understanding what the volcano might do next. Lava flows, however dramatic, tend to be the eruption's visible symptom. Fault movement is closer to the underlying diagnosis, because it reflects the actual mechanical stress state of the flank, rather than simply where magma happens to be emerging on a given day. There's also a longer scientific through line worth understanding, because Fiandaca hasn't suddenly appeared on researchers' radar in 2026. It's been a subject of dedicated study for decades precisely because of this exact behavior pattern. A 20-year data set of repeating earthquakes along the fault, collected between 2000 and 2019, and published through a collaboration between the University of Catania, INGV's Osservatorio Etneo, the University of Bologna, and the German Research Center for Geosciences in Potsdam, identified 4 structurally distinct portions of the fault system, each with different triggering behavior. That level of granular characterization exists precisely because Fiandaca's movements have proven predictive often enough to justify the sustained research investment. A seismic swarm along this fault in December 2015 followed abrupt deflation produced by 4 separate paroxysmal events at the Voragine crater that same month. Nearly the same pattern observed in miniature during the current August 2026 sequence, where fault movement followed weeks of intensifying eruptive activity at the same crater. None of this places nearby communities in confirmed immediate danger as of the most recent monitoring updates. INGV's alert status for the broader eruption has fluctuated between orange and red depending on ash output and lava effusion rates, but no evacuation orders beyond the localized closures near Piano Provenzano and the Marnev Road have been issued in connection with the fault reactivation specifically. Communities on Etna's slopes are accustomed to living alongside an active volcano, and the region's emergency management infrastructure, coordinated through Sicily's Civil Protection Agency and INGV's continuous monitoring network, is built specifically around interpreting exactly this kind of ambiguous signal without either dismissing it or overreacting to it. What makes this moment worth paying attention to isn't a single dramatic number or a confirmed prediction of imminent disaster. It's the convergence of several independent signals pointing in the same direction at once. A fault with a documented history of preceding significant volcanotectonic episodes, moving during an already unusually active eruptive year, immediately following weeks of intensifying activity at the same crater system that has repeatedly triggered fault movement in the past. Individually, each of those facts is manageable. Together, they're exactly the combination that has justified INGV's decision to treat this reactivation as more than routine housekeeping. For anyone trying to follow this story accurately as it develops, a few concrete markers are worth tracking, rather than relying on secondhand alarm. INGV's Osservatorio Etneo publishes regular activity bulletins documenting tremor amplitude, ash plume height, and lava effusion rates. And those bulletins are the most direct source for understanding whether the current sequence is escalating or settling. The aviation color code, the same system that jumped to red in late July, offers a quick, standardized read on explosive activity severity, independent of ground-level fault behavior. And any further movement along Pernicana specifically, whether measured through additional earthquakes, GPS ground deformation data, or visible surface fracturing, will be the clearest indicator of whether this particular reactivation was a footnote in an already busy eruptive year or the opening chapter of something the mountain hasn't done in nearly a decade. To place all of this in proper geological context, it helps to step back and consider what makes Etna such an unusual mountain in the first place. Standing over 300 meters tall on the eastern coast of Sicily, it's the tallest active volcano in Europe and one of the most continuously monitored volcanic systems anywhere on the planet. Unlike volcanoes formed at simple subduction boundaries, Etna sits in a tectonically complicated position near the boundary between the African and Eurasian plates, but also influenced by a broader network of strike-slip faults running through eastern Sicily. Research published in scientific reports map this network in detail, identifying a chain of onshore structures, including the Fiandaca, Trecastani, Acicatena, Santa Venerina, and Pernicana faults, all tied into a regional pattern of strike-slip tectonics that shapes where and how the volcano's magma finds its way to the surface. Pernicana sits at the northern edge of that network, distinguished from many of its neighbors by its transtensive character, meaning it accommodates both sideways slip and outward stretching simultaneously, a combination well suited to absorbing the eastward creep of Etna's mobile flank. That mobile flank is itself one of the more remarkable features of the mountain, and it's worth explaining plainly because it's central to why Pernicana matters so much. Much of Etna's eastern side isn't anchored to the rest of the volcanic edifice the way you'd expect a mountain slope to be. Instead, it behaves more like a large, slowly detached block, sliding gradually toward the Ionian Sea under its own weight and the pressure exerted by magma rising through the volcano's interior. This isn't a slow-motion catastrophe happening on human timescales. The movement is measured in centimeters per year under normal conditions, but it means the eastern flank effectively floats semi-independently of the rest of the mountain, bounded by fault systems on its margins. Pernicana forms the northern boundary of that unstable block, while other structures, including the Trecastagni fault, studied extensively through multi-parametric surveys of its dip-slip ruptures, help define the southern margin. Its lava tends to be relatively slow-moving and viscous enough that evacuation ahead of an advancing flow front is almost always achievable with adequate warning, which is precisely why INGV's monitoring infrastructure focuses so heavily on early detection of exactly the kind of precursor signals Pernicana provides. The danger from an event like this isn't typically sudden, catastrophic loss of life. It's localized structural damage to roads, buildings, and infrastructure directly along the fault trace, disruption to regional air travel from ash plumes, and the slower economic toll of repeated tourism disruption during peak season, all of which have already materialized to some degree during 2026's unusually active eruptive year. That said, complacency born from decades of manageable eruptions is exactly the risk INGV's careful, uncertainty-acknowledging language is designed to guard against. A volcano that has behaved predictably for generations can still produce a genuinely unusual event. And the researchers who spend their careers studying Pernicana are keenly aware that historical pattern matching only goes so far. The fault's role as a stress transfer conduit between the volcano's interior and its unstable eastern flank means that, in the right combination of circumstances, its movement could plausibly precede something more consequential than the road cracking and localized evacuations seen so far in August. Nobody currently monitoring the mountain is predicting that outcome as likely. But the entire reason this reactivation earned sustained coverage from INGV, rather than a brief mention buried in a routine bulletin, is that ruling it out entirely isn't something the available data currently supports either. The regional economic dimension of this story deserves its own explanation, because it's easy to underestimate just how much a mid-sized fault reactivation on a well-behaved volcano can ripple outward into everyday life across an entire region. Catania sits close enough to Etna that its airport, one of the busiest in southern Italy, operates under a permanent contingency plan for ash disruption, and 2026 tested that plan repeatedly. Diverted flights to Lamezia Terme, Palermo, Trapani, and Comiso weren't isolated incidents scattered across the year. They occurred in overlapping waves tied directly to each escalation in explosive activity at the Voragine crater, compounding through what should have been the peak weeks of Sicily's summer tourism season. That measured, proportionate reaction reflects decades of institutional experience managing a volcano that, for all its activity, has rarely required the kind of large-scale, sudden evacuations associated with less predictable volcanic systems elsewhere in the world. Comparing Etna's Pernicana Fault to hazard structures on other closely watched mountains around the world helps clarify what makes this particular case distinctive rather than simply another entry in a long list of volcanic fault systems. Many of the world's most dangerous explosive eruptions capable of generating pyroclastic flows that move too fast for effective evacuation once triggered. Etna's hazard profile is structured differently, distributed across its flanks through a network of faults like Pernicana, Fiandaca, and Tricastani, each acting almost like a pressure valve absorbing stress from different parts of the underlying magmatic system. This distributed structure is arguably part of why Etna, despite erupting far more frequently than almost any other volcano its size, has caused comparatively few direct fatalities in recent history. The hazard tends to announce itself gradually, through fault movement, ground deformation, and slow-moving lava, rather than erupting with the sudden violence of a stratovolcano whose magma system behaves more explosively. None of that distributed, relatively gradual hazard profile should be mistaken for an absence of risk, however, and researchers are careful to draw that distinction explicitly. The 2002 Presa landslide, triggered by Pernicana's reactivation that year, stands as a clear counterexample to any assumption that gradual equals harmless. Landslides triggered by fault movement on a volcanic flank can occur with very little advance warning once the underlying ground finally gives way, even if the fault movement causing the destabilization has itself been building gradually and been closely tracked for weeks beforehand. That's precisely the scenario INGV's continuous monitoring is designed to catch as early as possible. Not necessarily to predict the exact moment of failure, but to identify when ground deformation along a known unstable slope has crossed into a range where failure becomes meaningfully more likely, giving local authorities enough lead time to restrict access to the most vulnerable terrain. Looking specifically at what comes next for the current sequence, INGV's own public communications offer the clearest available roadmap. The agency's downgrade of the aviation alert level in mid-August was explicitly framed as reflecting current instrument readings rather than a guarantee against recurrence, language chosen deliberately to avoid signaling an all clear that the underlying data doesn't support. Tremor amplitude readings through mid-August showed unusual fluctuation even as overall levels remained comparatively low, a pattern that seismologists interpret as the volcanic system still actively adjusting rather than settling into a stable, quiet baseline. Whether that adjustment resolves quietly over the coming weeks or produces another visible escalation, whether along Pernicana itself, at one of the summit craters, or at a nearby structure like Fiandaca that has previously absorbed stress transferred from Pernicana's movement, remains the central open question driving INGV's continued close monitoring of the mountain. For readers trying to gauge the credibility of any specific claim circulating about this event, it's worth restating exactly which numbers are verified and traceable to INGV or peer-reviewed sources, since volcanic hazard stories tend to accumulate exaggeration quickly once they spread beyond specialist outlets. The magnitude, 3. 9. Earthquake on August 15th, and the subsequent 13 smaller events through August 20th are documented directly through INGV's seismic bulletins. The characterization of Pernicana as the northern boundary of Etna's mobile eastern flank comes from peer-reviewed research published in Communications, Earth, and Environment. The historical link between fault reactivation and the 1984, 2002, and 2018 episodes is drawn from published seismological analysis of those specific events, not retrospective speculation applied after the fact. And the explicit acknowledgement of scientific uncertainty about whether this reactivation precedes further escalation comes directly from INGV's own public statements, not from outside interpretation layered on top of a more definitive official position. Anchoring the story to those specific, sourced facts is what separates an accurate account of a genuinely significant geological event from the kind of inflated, single-number headline that tends to spread fastest and explain least. Etna has erupted more than almost any other volcano on Earth, and its eastern flank has been sliding toward the sea for as long as researchers have been measuring it. The Fiandaca Fault sits at the boundary of that slide, absorbing stress that has to go somewhere as the volcano breathes in and out with each eruptive cycle. What happened in mid-August 2026 wasn't unprecedented. The fault has moved before, many times, and most of those movements resolved without incident. What makes this instance worth watching closely is the same thing that makes any sentinel worth watching. It doesn't tell you exactly what's coming, only that something underneath is shifting, and that the people whose job it is to interpret that shift are choosing deliberately not to look away.